In the physical world, we conduct experiments to give us sensory outputs such as blips, bumps, stripes, pointed needles, numbers, and computer files. To explain these outcomes, we use terms like spacetime, energy, field, particle, spin, and charge. We describe these outcomes using mathematics. Spin is a concept in mathematics that can be represented in various ways. For instance, SU2, unit quaternions, and geometric algebra are different tools to describe the unusual behavior of half-integer spin. There is a direct analogy between the behavior of certain mathematical objects and the behavior of reality when a measuring device interacts with its environment. In general, we have 1. Symmetries belonging to an object, and 2. Objects connected by a symmetry. A property of an object can be an object too, so the spin of an electron has symmetries. The elementary particles we observe in nature are expressions of the symmetries that nature possesses. Quantum field theory is currently the most accurate model we have to understand reality. Its description for a fermion consists of 3 things. Firstly, there's a spinor field where every point in space-time has a 4-component complex spinor assigned. Secondly, there's a description of the energetic composition of the spinor field in the shape of a Lagrangian. Finally, coupled differential equations are derived from the Lagrangian to describe the behavior of the spinor field in space-time. The Lagrangian has the gamma matrices that represent the SU2 symmetry and half-integer spin behavior. The standard model of particles comprises the elementary particles that have been discovered so far. We affirm their existence as each particle possesses a distinct, identifiable, and reproducible signature in our experiments. Elementary particles are themselves building blocks for other stuff. We distinguish 2 types, fermions and bosons. The bosons are the forces, or better, the interactions between fermions. The fermions are the particles that move under the influence of these bosons. If, for instance, 2 fermions collide, we say that they have exchanged a boson that made the particles move in new directions. In SpaceTimeCapital, there are no particles and there are no interactions. There is only elastic SpaceTimeCapital movement. In a way, SpaceTimeCapital places fermions and bosons on equal footing, because they are all contortions of the same fabric. The scientific method model of separation between spacetime and energy, or spacetime and probability field, or spinor field, gives rise to the standard model, general relativity, and quantum mechanics. In the scientific method model of separation, we know of interactions or forces working on particles. Forces appear to exist because separation appears to exist. Whenever particles are distinguished, a description of any interactions between them becomes necessary. Forces or interactions emerge from distinction. I repeat, interactions emerge from distinction. The interactions, the elementary bosons, are relatively easy to comprehend. They move with the speed of light and have spin 1. Spin is a weird property, so even spin 1 is weird. But fermions have spin 1/2, which is even weirder. Elementary particle spin is essentially a mathematical thing that we do not understand for fermions as a physical thing yet. Some physical descriptions to demonstrate the principle and to give a feel for the weirdness are the Dirac string trick, the bell trick, Tangloids, and the Balinese cup trick. In geometry, one rational number to probe straight lines is enough. To probe bending and circles and oscillatory movement, two numbers in a specific relation are required. We call those pairs of related rational numbers a complex number. For example, a unit complex number can be used to describe properties such as helicity or spin alignment, and polarization or the orientation of the electric field of photons. To distinguish fermions from bosons and to describe half-integer spin, we need not one but three rational numbers for SU2. Unit quaternions have these three rational independent numbers too. To put it simply, when we rotate a boson by 360 degrees, it remains the same particle. However, when we rotate a fermion by 360 degrees, it becomes the negative of itself. To get back to the original fermion, we need to rotate it by another 360 degrees, so 720 degrees in total. No one seems to understand it in terms of underlying complete machinery. We understand the algebraic constructs that behave in this weird way, so to speak. And the measurement results behave like the number constructs do on paper. For instance, in 1922, the Stern-Gerlach experiment demonstrated the quantization of angular momentum and the discrete nature of spin. An electron is an example of an elementary particle with spin 1/2. Its properties, from our perspective, are: electrons possess mass, charge and spin. Two identical electrons cannot be in the same state. This is called Pauli's exclusion principle. Electrons follow Fermi-Dirac statistics, which include the Pauli exclusion principle. Electrons exhibit wave-particle duality. Electrons are mathematically considered point particles. In an atom, electrons have 4 quantum numbers. These are known as principal, azimuthal, magnetic and spin. Electrons interact with photons, can quantum entangle and quantum tunnel. Electrons are responsible for various phenomena in materials such as electrical and thermal conductivity, magnetism, magnetic resonance, electron-phonon scattering, and the list goes on and on. Its antiparticle is a positron. The concept of spin in quantum mechanics is abstract and has perhaps no classical analogue. The word spin seems a bit misleading. This all sounds very weird, and it should, I suppose, because we have to describe something very weird. These electron spinners describe two different states, one which we call spin up and one which we call spin down. If we rotate a spinner half a turn using these complex numbers, we rotate it from spin up into spin down. In the real world, this complex half turn would seem like a 360-degree full turn. Another 360-degree turn gives us back a spin-up spinner. So in other words, electrons have a property called spin that is so weird that by intuition we have to sort of turn an electron 720 degrees to get back the same electron. In mathematics, we say that SU2 is the double cover of SO3. One thing is for sure: the mathematics behaves in the same way as reality does in our experiments. We just seem unable to wrap our intuition around it. In reality, we notice these objects with a property that is sometimes up and sometimes down. The object has up-downness in a superposition of states. If we construct a mathematical object that has this twofold way, this double cover, we can use it as an analogy for the real-life up-down property of the object. We suspect that there is a classical explanation for the property of half-integer spin. The SpaceTimeCapital contortion, called the resonance carrier ball, with harmonic resonances and an inner continuous belt trick rotation, may for the first time provide a more classical feel at the cost of losing our perspective. The animations are discrete impressions of the moving belt trick rotation, continuous space inside the carrier ball. Imagine more and more strings connecting to more and more shrinking white and black cube in the middle. Physics would become a two-layer paradigm, with one layer for reality, with the physics of one elastic space-time capital, and one layer for our perspective on reality, with the physics of the scientific method, general relativity, quantum mechanics, and the standard model. That is why we should carry out the research proposed in the book in the description below.